Hello, I'm Ivan. Previously Bruno introduced you to the classification prior networks and ensemble distribution distillation. In this video, I'll expand this topic to regression. For regression tasks, we usually take something like mean squared error loss and optimize our network only to be closer to the targets. But this approach will not give us any information about uncertainty measures, about how confident our model is in its predictions. To calculate the uncertainty measures, we can use probabilistic models. For example, we can consider that targets are produced by normal distribution. In this case, neural network will predict mean and variance. Mean will be responsible for answer, and variance will be responsible for confidence of our model. And we will use negative log likelihood loss to optimize this. From previous videos, you know that ensembles with random initial seeds allow us to calculate uncertainty measures. In case of Gaussian ensembles, if we are in domain and a prediction task is simple, then each model in our ensemble is confident, and their predictions match. Variance is small, and ensemble predictions of mean are agreed with each other. In the middle, you can see a case with high data uncertainty. It means that for this case, it is hard to make a decision about a result. Maybe we have a lot of noise. For classification, there could be a class overlap here. Our ensembles agree with each other about mean of the distribution, but their variance is high. So each model is not confident in its predictions. Finally, case with high knowledge uncertainty. You can see that ensemble predictions here are quite chaotic. They are both models with high and low variance, and the models are not agreed about the mean of the distribution. Such behavior means that the input data is out of distribution and our models are not ready to work with it. We can also write these uncertainty measures formally by using entropy of expected answers over the ensemble and expected entropy. Note that here we take expectation over possible outputs of the ensemble. So here we consider that there is a distribution over normal distributions that describes correct behavior for each example. And we model this distribution with our ensemble. That brings us to the regression prior networks. The main idea is as follows. Let's consider a distribution over the parameters of normal distribution and use it to obtain meaningful uncertainty measures and improved accuracy of Gaussian ensemble. Let's look more precise on it. Firstly, we have our usual Gaussian. Secondly, we choose some distribution over normal distributions. In our work, we consider normal Wishart distribution. It has its own parameterization. Basically, it is a product of normal distribution over mean and Wishart distribution over variance or precision. There are methods to train such network from scratch, but they are quite complicated and usually do not work better than ensembles of Gaussians. So we will not discuss them in this presentation. Instead, we will focus on ensemble distribution distillation. Suppose that we have some ensemble of Gaussian models with desired behavior and we want to use it. We may have a problem with this situation. Ensemble methods are quite greedy. If we have 20 models, we need to run them all on the same input to make a prediction. So we need 20 times more computational time than one model. Ensemble distribution distillation allows us to distill an ensemble of models into one prior network that will incorporate the behavior of the whole ensemble. It saves improved performance and uncertainty measures of ensemble, while is as fast as one model during inference. It is simple to use ensemble distribution distillation. Firstly, you need to train an ensemble, and secondly, you need to distill it into a prior network on some dataset via log likelihood. It could be a trained dataset with data augmentations, or some other dataset even without labels. Let's look at the examples of ensemble distribution distillation usage. In our article, Regression Prior Networks, we used molecular depth estimation task. In this task, you have images and you need to predict depth map for each image. Here you can see an example of work of our methods. We have an input image, our predictions of depth, total uncertainty, and knowledge uncertainty for each pixel. There are two methods here, ensembles and ensemble distribution distillation. Note that ensemble distribution distillation predictions are quite similar to the whole ensemble. This is on top and on the bottom. While it uses much less memory and computational time during inference. With this model, we can understand how confident the model is in its predictions for each pixel. And also, we can easily find out-of-domain regions of the image. And afterwards, provide them to labelers or create a special behavior for them. More information about this you can see in our video about uncertainty applications in production. On the next slide, we have error image instead of prediction image. You can see that error is correlated with total uncertainty, so our model understands where it is wrong. The same setup of prediction could be used to any regression task. You can train an ensemble and afterwards incorporate its behavior into prior network to save inference time. Let me go over the key points of the presentation. We expanded ensemble methods for regression task, became familiar with normal Wishart prior networks, and remembered the essence of ensemble distribution distillation methods. That's all for now. If you have any questions, feel free to contact me. See our next videos. Thank you for your attention.